Hello, today we will see SQL tuning. Let's have a look on objective of the session. First, describe how the optimizer is used for SQL tuning. Explain the concept of plan stability. Explain the use of stored outlines. Describe how hints are used. Use of SQL trace and TKPROF utility. So, SQL utility and TKPROF utility. In SQL tuning, we will see how to tune the SQL queries so that our output will be less system utilization and faster retrieval of data. Let's see phases of a query. How a query will process. When a user starts data retrieval operation, the user's SQL statement goes through several sequential steps that together constitute query processing. A user's SQL statement goes through the parsing, optimizing, and execution stage. Parsing. Parsing primarily consists of checking the syntax and semantics of the SQL statement. The data dictionary is consulted to ensure that the tables and the individual columns that are referenced in the query do exist, as well as all the object privileges. In addition, the column types are checked to ensure that the data matches the column definitions. The statement is normalized so it can be processed more efficiently. The query is rejected if it is incorrectly formulated. Once the parse tree passes all the syntactic and semantic checks, it is considered a valid parse tree, and it's sent to the logical query plan generation stage. All these operations take place in the library cache portion of the SGA. Next phase is optimization. During the optimization phase, Oracle uses a cost-based optimizer (CBO) to choose the best SS method for retrieving data. Using statistics that we provide and any hint specified in the SQL query, the cost-based optimizer produces an optimal execution plan for the SQL statement. The optimization phase can be divided into two distinct parts. First, the query rewrite phase. Second, the physical execution plan generation phase. Now, query rewrite phase. The parse tree generated in the parsing stage is input for this phase. The parse tree is converted into an abstract logical query plan. The various nodes and branches of the parse trees are replaced by operators of relational algebra. Execution plan generation phase. The logical query plan is transformed into a physical query plan. The optimizer may be faced with a choice of several algorithms to resolve a query. Last phase, that is query execution. The optimized query is executed in this phase. The SQL execution engine takes the execution plan provided by the optimization phase and executes it. Optimizer modes. Cost-based optimization. Earlier, before 10G, there is one more mode named rule-based optimizer. But from Oracle 10G and in Oracle 11G, only optimization mode left is cost-based optimizer. Now, in cost-based optimizer mode, the optimizer examines each statement and identifies all possible access paths to the data. It then calculates the resource cost of each access path and chooses the least expensive one. The costing is based mainly on the number of logical reads. The cost-based optimizer is statistics driven in that it uses statistics generated for the object involved in the SQL statement to determine the most effective execution plan. The cost-based optimizer is used if any object in the SQL statement has had statistics generated for it. We should use this optimizer mode for new applications, particularly if they use the parallel query feature. The CBO uses statistics on tables and indexes. The most efficient way, according to the CBO, is the least costly access path. Cost being defined in terms of the input-output and the CPU expended in retrieving the rows. We can examine these access paths by using tools such as the explain plan. Some drawback of the cost-based optimizer. The CBO isn't fixed across all Oracle versions. Execution plan can change over time as version changes. So we can also use some stored outlines, so the optimizer always uses a known plan to maintain the plan stability. Next, application developers may know more than the CBO when it comes to choosing the best access path. Application developers know the needs of the user, of which the CBO is completely unaware. This could lead to a situation where the CBO may be optimizing throughput when the user would rather have a quick set of results on the screen. By using hints such as first_rows_n, we can overcome this drawback in the CBO. The CBO depends enormously on correct statistics gathering. If the statistics are absent or outdated, the optimizer can make poor decisions. Now, what does the optimizer do? The CBO performs several intricate steps to arrive at the optimal execution plan for a user query. The original SQL statement is most likely transformed, and the CBO evaluates alternative access paths. If table joins are necessary, the optimizer evaluates all possible join methods and join orders. The optimizer evaluates all the possibilities and arrives at the execution plan. It deems the cheapest in terms of total cost, which includes both input-output and CPU resource usage cost. Choosing your optimization mode. Recon can also optimize the response time, which usually means using the fewest resources to get the first rows. The value we set for the optimizer_mode initialization parameter is the default mode for the Oracle optimizer. We can use any of the following three modes for the optimizer with the CBO: all_rows, first_rows_n, first_rows. If we want to set this at the instance level, then we have to specify the parameter optimizer_mode in the parameter file. At the session level, we can do this by using alter_session command. If we want that only particular SQL query should use these optimizer modes, then in that query we will use hints. Optimizer plan stability. For every query, the optimizer prepares a tree of operation called an execution plan that defines the order and methods of the operation that the server follows to execute the statement. Because the optimizer may have incomplete information, sometimes the best possible plan is not chosen. In these cases, you may find it worthwhile to influence the optimizer's plan selection by rewriting the SQL statement, using hints, or by using other techniques. Once satisfied, we may want to ensure that the same tuned plan is generated whenever the same query is recompiled, even when factors that affect optimization may have changed. Now, Oracle provides the user with the means of stabilizing execution plans across Oracle releases, database changes, or other factors that normally causes an execution plan to change. We can create a stored outline containing a set of hints used by optimizer to create an execution plan. Optimizer_features_enable parameter. This parameter allows a version of the Oracle server to run with the cost-weight optimizer features of an earlier version. This parameter should be left as default, which is in the current release. Plan equivalence. Plan stability relies on exact textual matching of queries when determining whether a query has stored outline. This is the same matching criteria used to determine whether an execution plan in the shared pool can be reused. Stored outlines rely partially on hints that the optimizer uses to achieve stable execution plans. Therefore, the degree to which plan remains equivalent is dependent on the capabilities of the hints the plan uses. The execution steps included in a stored outline include row access methods, join orders, join methods, distributed accesses, view, subquery merging. Distributed access does not include the execution plan on the remote node. Plan stability. These plans are maintained through many types of database and instance changes. Therefore, If we develop application for mass distribution, we can use stored outline to ensure that all our customers access the same execution plan. For example, if a schema is changed by adding an index, the stored outline can prevent the use of new index. Creating stored outlines. The server can create outlines automatically, or we can create them for specific SQL statements. Outlines use a cost-based optimizer because they rely on hints. Categories. Stored outline can be grouped by categories. The same SQL statement can have a stored outline in more than one category. For example, we may want to have an OLTP category and a DSS category. If a category name is omitted, outline are placed in the default category. Create stored outline parameter. Oracle creates stored outlines automatically for all executed SQL statements when we set create stored outlines to true or to a category name. When set to true, the default category is used. We can deactivate the process by setting the parameter to false. When this parameter is used, the outline names are also generated automatically. Create outline command. We can also create stored outline for specific statement by using the create outline command. One advantage of this approach is that we can specify a name for the stored outline. Using stored outlines. If use_stored outlines is set to true, then outlines from the default categories are used. If this parameter is set to a category name, then the outlines from that category are used. If there is no matching outline in that category, but there is one in the default category, then that outline will be used. The statement must match the text of the statement in the outline. They are compared using the method of comparing cursors in the shared pool. This means that hints in the outline have to be used in the statement text to cause a match. Values in bind variable do not need to match. To determine SQL statement execution plan, Oracle uses the following logic. Statement is compared to statements in the shared pool for matching text and outline category. If no matching statement is found, the data dictionary is queried for a matching outline. If matching outline is found, Oracle integrates the outline into the statement and creates the execution plan. If no outline is found, the statement is executed using normal methods. If an outline specifies the use of an object that can't be used, for example, it references an index that no longer exists, the statement will simply not use the hint. To verify that a stored outline is being used, the explain plan for statements need to be compared when running with and without use_stored outlines set. Next, using private outlines. The use_private_outlines parameter let us control the use of private outlines. A private outline is an outline seen only in the current session and whose data resides in the current parsing schema. Any changes made to such an outline are not seen by any other session on the system, and applying a private outline to the compilation of a statement can only be done in the current session with the use_private_outlines parameter. Only when we explicitly choose to save our edits back to the public area, they are seen by the rest of the users. The outline is cloned into the user's schema at the onset of the outline editing session. All subsequent editing operations are performed on that clone until the user is satisfied with the edits and chooses to publicize them. In this way, any editing done by the user does not impact the rest of the user community, which would continue to use a public version of the outline until the edits are explicitly saved. When a private outline is created, an error is returned if the prerequisite outline tables to hold the outline data do not exist in the local schema. These tables can be created using the dbms_outline_edit.create_edit_tables procedure. We can also use the utle edit ol.sql script. Prerequisites using private outline. When the use private outline parameter is enabled and an outlined SQL statement is issued, the optimizer retrieves the outline from the session private area rather than the public area used when use store outlines is enabled. If no outline exists in the session private area, then the optimizer will not use an outline to compile the statement. Editing stored outlines. Assume that we want to edit the outline Dave01. So the steps are: first, connect to schema from which the outline statement can be executed, and make sure that create any outline and select privileges have been granted. Create outline editing tables locally with the help of a package dbms_out_ln_edit. So the procedure will be dbms_out_ln_edit dot create_edit_tables. Second step, clone the outline being edited to the private area using the following: create private outline p_dave01 from dave01. Third step, edit the outline either with the outline editor in Enterprise Manager or manually by querying the local $hints table and performing DML against the appropriate hint tables. To change the join order, use the procedure dbms_out_ln_edit dot change_join_ps. If manually editing the outline, then resynchronize the stored outline definition using the following so-called identity statement: create private outline p_dave01 from private p_dave01. Next step, we can also use another procedure refresh_private_outline, or we can do alter system flush shared_pool to accomplish the same task. Now test the edits. Set use_private_outline to true and issue the outline statement, or run explain plan on the statement. If we want to preserve these edits for public use, then publicize the edits with the following statement: create or replace outline dave01 from private p_dave01. After that, disable the private outline usage by setting again the parameter use private outline to false. Maintaining stored outlines. Use procedures in the outln_pkg package to manage stored outlines under categories. These procedures are: first one is drop_unused. It is used for drops outline that have not been used since they were created. Second procedure is drop_by_cat. It will drop outlines assigned to specific category name. Update_by_cat reassigns outlines from one category to another. Outlines can also be managed with the alter or drop outline command. Plans may be exported and imported by exporting the outln schema, where all outlines are stored. Outlines can be queried from tables in the schema. $. Outline name, category, creation, timestamp, and the text of the statement will be found in this view. $hints. The hints for the outline present in the $. Dynamic view. The equivalent data dictionary views are dba_outlines and dba_outline_hints. Because the user outln is automatically created with the database, its password should be changed. Using hints in a SQL statement. We may know information about our data that the optimizer does not know. For example, we may know that a certain index is more selective for certain queries. Based on this information, we may be able to choose a more efficient execution plan than the optimizer. In such a case, use hints to force the optimizer to use the optimal execution plan. For example, in the example given here, there is an index on the cust_gender column of the customer table. There are very few male customers, therefore the statement runs faster using the gen_IDX index. In order to force the optimizer to use the index, it is put in a hint, that is slash star and plus. Overview of diagnostic tools. Numerous diagnostic tools are available for evaluating the performance of a SQL statement and PL/SQL modules. Each provides a developer or DBA with a varying degree of information. To identify the SQL query which requires tuning, we can use various Oracle provided views and utilities such as Automatic Database Diagnostic Monitor, Automatic Workload Repository, $SQL View, $SQL Area View, $SQL Text View, SQL Trace, TKPROF Utility, Oracle SQL Analyze, etc. Explain plan. This is executed within a session for a SQL statement. SQL Trace. This utility provides detailed information regarding the execution of SQL statements. TKPROF. This is an operating system utility that takes the output of a SQL Trace session and formats it into a readable format. AUTOTRACE. This is a SQL Star Plus feature. AUTOTRACE generates an execution plan for a SQL statement and provides statistics relative to the processing of that statement. Oracle SQL Analyze. This is part of the Oracle Enterprise Manager tuning pack, and it provides a powerful user interface for tuning SQL statements. Automatic Workload Repository, or in short AWR. The AWR was designed by Oracle as a replacement for the traditional StatusPack utility, which helps us gather database performance statistics. AWR generates snapshots of key performance data such as system and session statistics, segment usage statistics, time model statistics, and high load SQL statistics. It stores the snapshots in the sysux table space. By default, the database will generate a performance snapshot every hour. We can customize the snapshot interval, the types of statistics the AWR collects, and the length of time the snapshots are retained in AWR. Using the dbms_workload_repository package to manage the AWR snapshot. We can use dbms_workload_repository package to create, drop, and modify snapshots, as well as to create and drop snapshot baselines. For creation of AWR reports, Oracle provides a script named AWR RPT, which is located in Oracle home/rdbms/admin directory, to generate summary reports about the statistics collected by the AWR facility. The results of running the AWR RPT.SQL script are very similar to the output of traditional StatusPack reports. In order to run an AWR report, we must have the DBA privileges. Automatic Database Diagnostic Monitor, ADDM. It automatically analyzes performance data for us. Every time the AWR takes a new snapshot, ADDM runs automatically, does its top-down system analysis, and reports its finding on the database control home page. ADDM output consists of description of each performance problem it identifies along with the recommended action. The recommendations are ranked by the expected benefit of implementing each of them. Now some of the problems that ADDM diagnoses. The ADDM analyzes the AWR snapshots every hour by default. It comes up with the performance recommendation and ranks them in terms of the expected benefit of implementing the various actions. These are some of the key problems that ADDM diagnoses. Expensive SQL statements, input-output performance issues, locking and concurrency issues, excessive parsing, resource bottlenecks, undersized memory locations, connection arrangement issues, etc. We can view the ADDM analysis reports in three different ways. First one is, we can use the Oracle provided ADDM RPT.SQL script to create an ad hoc ADDM report for the time period covered by any pair of snapshots. We can use the dbms_advisor package and create an ADDM report by using the create report procedure. Third method is we can use the OEM, that is Oracle Enterprise Manager, to view the performance findings of the stored ADDM reports, which are proactively created each hour after the AWS snapshots. Next is Explain Plan. The Explain Plan facilities help us to tune SQL by letting us see the execution plan selected by the Oracle Optimizer for a SQL statement. During SQL tuning, we may have to rewrite our queries and experiment with the optimizer hints. The Explain Plan tool is great for this experimentation, as it immediately lets us know how the query will perform with each change in the code. Because the utility gives us the execution plan without executing the code, so we save ourselves from having to run unintended software to see if the changes are beneficial or not. Understanding an Explain Plan is critical to understanding query performance. It provides a window into the logic of the Oracle Optimizer regarding its choice of execution plans. The output of Explain Plan tool goes into a table, usually called plan_table, where it can be queried to determine the planned executions of the statements. A walkthrough of an Explain Plan output takes us through the steps that would be undertaken by the CBO to execute the SQL statement. The Explain Plan tool indicates clearly whether the optimizer is using an index or not. Explain Plan tool indicates clearly whether the optimizer is using an index or not. It also tells us the order in which the tables are being joined and helps us to understand our query performance. Oracle creates a plan_table as a global temporary table, so all the users in the database can use it to save their Explain Plan output. However, we can create a local plan table in our own schema by running the utlx plan.sql script, which is located in the Oracle home/rdbms/admin directory. Other way of displaying Explain Plan results. We can also use the dbms_explain package to display the output of an Explain Plan statement in an easy readable format. Here is an example that shows how to use the dbms_explain package to produce the output of the most recent Explain Plan statement. In this slide, first of all, we are creating a local plan table by running the script utlexplain. After that, we are granting all the access on that table. Then we are creating one public synonym. After that, we are executing one query and creating Explain Plan for that. There are three methods for see the data inside the plan table. One is directly querying the plan_table with the help of select statement. Second is by running these two scripts, utlxpls and utlxplp. The execution plan of a query is a description of how Oracle will implement the retrieval of data to satisfy a given SQL statement. It is nothing but a tree which contains the order of steps and relationship between them. The basic rule of execution plan tree are: an execution plan will contain a root which has no parent. A parent can have one or more children, and its ID will be less than the child's ID. A child can only have one parent. It is indented to the right. In case of many childs, it will have the same indentation. Using the rule above, we can say operation 0 is the root of the tree. It has one child, operation 1. Operation 1 has two children, which is operation 2 and 4. Operation 2 has one child, which is operation 3. Here is the graphical representation of the execution plan. If we read the tree, in order to perform operation 1, we need to perform operation 2 and 4. Operation 2 comes first. In order to perform 2, we need to perform its child operation, that is 3. And in order to perform operation 4, first we need to complete the operation 2. Now operation 3 accesses department table using index unique scan and passes the row ID to operation 2. Operation 2 returns all the row from department table to operation 1. Operation 1 performs operation 4 for each row returned by the operation 2. And operation 4 performs a full table scan, that is table access full scan, and applies the filter e.department number is equal to 10 and returns the row to the operation 1. After that, operation 1 returns the final results to operation 0. On the left hand side, we can see how a plan table looks like. When we explain a plan for a query, and the data for the explained plan is stored in the plan table. Next is SQL Trace. SQL Trace enables us to track the following variables: CPU and elapsed time, passed and executed counts for each SQL statement, number of physical and logical reads, execution plan for all the SQL statements, library cache hit ratios. SQL Trace files can capture the SQL execution for dynamic SQL. That is, if any application has a lot of dynamically generated SQL, the SQL Trace utility is ideal for tuning the SQL statements. Some trace initialization parameters: timed underscore statistics, max underscore dump underscore file underscore size, user dump test. These parameters are dynamic session parameters and can be changed using alter session command. After setting these parameters at system level, we must restart the database. Now, the timed underscore statistics parameter is dependent upon statistics underscore level parameter. It has 3 possible values which affect the timed statistic parameter, that is typical, all, or basic. Time statistics default is false if statistics level is set to basic. Next is user dump test. This must fully specify the destination for the trace file according to the conventions of the operating system. The default value is the default destination for system dumps on the operating system. Enabling or disabling SQL Trace. SQL Trace can be enabled in the following 2 ways: using alter session command, like alter session set SQL Trace is equal to true. Second is using dbms underscore session package. We execute a procedure, execute sys dot dbms underscore session dot set underscore SQL underscore trace as true. Alter session set SQL trace is equal to false. Once the tracing is set to on, any SQL statement issued during that session is traced. The output of the tracing is stored in the udump directory defined by using user underscore dump underscore dest parameter. The file name has the format db underscore name underscore aura underscore nnn dot trc. Formatting the file. TKPROF. TKPROF is one of the most useful utilities available to the DBAs for diagnosing performance issues. It essentially formats a trace file into a more readable format for performance analysis. The DBA will use TKPROF and session tracing when the database or a particular session is having performance problems. Session tracing and TKPROF can be used to see exactly what is happening on the database, enabling the DBA to take corrective actions. Analyzing results. It compares the number of parses to the number of executions. Searches for SQL statements that do not use bind variable. We can identify those statements that perform full table scans, multiple disk reads, and high CPU consumption. TKPROF accepts as input a trace file produced by the SQL Trace facility, and it produces a formatted output file. After the SQL Trace facility has generated a number of trace files, we can run TKPROF on each individual trace file, producing a number of formatted output files, one for each session. It concatenates the trace files and then runs TKPROF on the result to produce a formatted output file for the entire instance. TKPROF does not report commits and rollbacks that are recorded in the trace files. If simply TKPROF is written on the prompt, then we will see a complete listing of all the parameters that we can specify when we invoke TKPROF. Interpreting TKPROF result. Each TKPROF output file contains a header, body, and a summary section. The header simply displays the trace file names, definition, and sort options selected. The body contains the performance matrices for SQL statements. The summary section contains an aggregated of performance statistics for all SQL statements in the file. TKPROF will collect the following statistics. First one is count, that is the number of times the statement was parsed or executed and the number of fetch calls issued for the statement. CPU, processing time for each phase in seconds. Elapsed time in seconds. This is not usually very helpful because other processes affect the elapsed time. Disk, physical data blocks read from the database files. Query, logical buffer retrieved for consistent reads. Current, logical buffer retrieved in current mode. And then rows processed by the outer statement. The sum of query and the current is the total number of logical buffers assessed. Here we can see on the right hand side the sample TKPROF body. It has shown the query for which it has generated this output. Number of parses, execute, fetches, CPU time, counts, elapsed time, etc. SQL Plus AUTOTRACE. It can be used instead of SQL Trace. The advantages in using AUTOTRACE is that we do not have to format a trace file, and it automatically displays the execution plan for the SQL statement. However, AUTOTRACE does parses and execute the statement, whereas explain plan only parses the statement. The steps for using AUTOTRACE are: first, create the plan table using the utl explain.sql script. Second, create the plus trace role by executing the plus trce.sql script. This grants select privileges on $view to the role and grants the role to the DBA role. Grant the plus trace role to the users who do not have the DBA role. Third, use AUTOTRACE. If we select its value as on, then it produces a result set and explain plan and list all the statistics. In the trace only mode, it displays the explain plan and the statistics. We will not see the result set, although the statement is executed. On explain plan, displays the result set and explain plan results without the statistics. Trace only statistics, displays the statistics only. Managing statistics. We collect statistics on an object with the analyze command. Although the cost-based optimizer is not sensitive to minor changes in volume or selectivity, we may want to collect new statistics periodically on frequent modified tables to ensure that the optimizer is using recent accurate information. Using the analyze command to collect new statistics overrides any existing statistics in the data dictionary and flushes any related execution plans from the shared pool. The dbms_starts package contains several procedures that allows an index, table, schema, or database to be analyzed. This package also enables us to gather most of the statistics with a degree of parallelism. Now, statistics accuracy. Compute. It calculates exact statistics. It performs a full table scan and several calculations. For a large table, this operation may take long time. Estimate. We estimate statistics with this option. If we use this option with a suitable sample of data, it is almost as accurate as the compute option. Delete. We clear out statistics with this option. We do not need to use this option before reanalyzing an object because existing statistics are overwritten. Next is for clause. The for clause offers the following options. For table, it restricts the statistics collected to a table statistics only rather than table and column statistics. For column, it restricts the statistics collected to only column statistics for the specified columns rather than for all the column and attribute. For all columns, it collects column statistics for all the columns. Next is for all indexes, specifies that all indexes associated with the table will be analyzed. If we insert local, like for all local indexes, then it specifies that all the local index partitions are analyzed. Size clause. The size clause specifies the maximum number of histogram buckets. Default value is 75 and the maximum value is 254. We can use the following packages to see the data. Gather _ table _ stats, it will gather the statistics on a table if we don't want to use the analyze command. Gather index stats for index gathering, gather schema stats, gather database stats for the full database stats. Table statistics. Each table maintains a high watermark in the segment header block. The high watermark indicates that the last block that was ever used for the table. When the Oracle server performs full table scans, it reads all the block up to high watermark. Note that the high watermark is not reset when rows are deleted from the table. The dbms _space dot unused _space procedure can also be used to find the high watermark and the number of blocks above the high watermark if analyzing a table is impossible or undesirable. We can see the data for a table in a db_table data dictionary view. Index. The index clustering factors is an important index statistics for the cost-based optimizer to estimate index scan costs. It is an indication of the number of logical data block visits needed to retrieve all table rows by means of the index. If the index entries follow the table row order, this value approaches the number of data blocks. On the other hand, if the index entries randomly point at different data blocks, the clustering factor should approach the number of rows. By looking at index statistics, we can know which query is using index and which is not, and using an index is helpful for a query or not. More data about the index on a table can be found in the data dictionary view db_indexes. The column statistics. For the column statistics, we use user_tab_call_statistics data dictionary view. It offers a relevant subset of the column displayed by the user tab column view. So by looking at the column statistics, we can also tune our SQL statements. SQL Tuning Advisor. If we have identified bad SQL, Oracle Database 10G offers a new SQL Tuning Advisor. It has the following features. It advises on improving the execution plan. It provides a reason for the SQL improvement recommendations. It benefits us. We can expect by following the advisor advice. And details of the command to tune the misbehaving SQL statement. Using the SQL Tuning Advisor on SQL statement. It is usual for the advisor to take SQL statements from places such as new SQL statements. When working with the development database, this may be our best source of SQL statement. high load SQL statement, SQL statements from the AWR, SQL statements from the database cursor caching. The advisor can tune sets of SQL statements called SQL tuning sets, that is STS. An STS is a set of SQL statements combined with the execution information, which includes the average elapsed time. An STS has the advantages of capturing the information about a database workload, as well as allowing us to tune several large SQL statements at once. SQL Tuning Advisor in practice. We can use the SQL Tuning Advisor through packages or through the web interface of the OEM database control, using the dbms_SQL tune package to run the SQL Tuning Advisor. The main SQL package for tuning SQL statement is dbms_SQL tune. Now we must have the advisor privilege to use dbms_SQL tune package. How the SQL Tuning Advisor works. As mentioned previously, the optimizer will try to find the optimal execution plan for each statement we provide. However, this process happens under production conditions, so the optimizer can only devote a short amount of time to working out a solution. The optimizer uses heuristics to generate an estimate of the best solution. This is called the normal mode of the optimizer. We can also run the optimizer in tuning mode, which means that optimizer carries out in-depth analysis to come up with the way to optimize execution plan. While in this mode, the optimizer can take several minutes and produce recommendations instead of the best SQL execution plan. We in turn use these recommendations to optimize the SQL statements execution plans. We get the added advantage of the advice that details the rationale behind the recommendation and what we will gain from implementing them. The Oracle optimizer running in the tuning mode is called the Automatic Tuning Optimizer. The ATO, that is Automatic Tuning Optimizer, does the following tasks: statistics analysis, SQL profiling, assess path analysis, SQL structure analysis. It needs to choose the most efficient algorithm to answer a query and perform the operations. In addition, optimizer determines the order in which it will perform these steps. Now, to manage our automatic SQL tuning efforts, we can use the following views: dba_advisor_task, dba_advisor_findings. We can see the recommendation in the db_advisor_recommendations, and so on. So by looking on these views, we can know what we need to do for tuning of a SQL statements. That's all about the SQL tuning. Thank you.